Yeah, she always has a lot of students. All right, go back to my little spill again. Y'all can hear since I forgot to record. So we're looking at kinetics, which is going to be how quickly a reaction occurs. Thermodynamics, which will be later, will tell us if the reaction occurs, but on this unit, we're seeing whether something or how fast something will occur as far as a reaction goes. All right, let's see if I can remember the stuff there. So we're going to look at some factors that affect the reaction rate, and some of them are kind of just common sense. The things that are going to affect the reaction rate is going to affect how often and forcibly the atoms or the molecules or the elements are able to collide with each other. The more often they're able to collide with each other and collide correctly with each other, that's going to increase the rate. So one thing that would affect it is the nature of the reactant. So if you can kind of think about the different phases of matter and what their kinetic energy is, it will come into play as far as the reaction rate goes. So if we think about the different phases, a solid is going to have the lowest kinetic energy. So it's going to have the least possible collision. So it's going to be slower than something that's a liquid or something that's aqueous. And then that's going to be a little slower than gas. So in the same order that their kinetic energy is as far as the particles go, that's going to also affect their rate of reaction. So something like if I had potassium sulfate and barium nitrate and I just stuck those two solids together, nothing's going to happen. If I, dissolved them in the aqueous solution and they were set to ions, then that reaction is going to occur very quickly. Another thing is the identity. What exactly is reacting? So usually ions of opposite charge, so that usually is if they're in the aqueous solution, will react very quickly. Also, the more bonds between the atoms in a molecule, the slower the reaction. And the reason that is all those bonds are going to have to be broken to kind of break that molecule up into its little bits or its little parts. So then those parts can try to collide with each other to form the new reactants. So it makes sense that the more bonds they have to get through, the slower that's going to be as far as the reaction rate goes. All right. Continuing on with that. So we're going to look at the concentration of the reactants, which it makes sense. If you increase the concentration of the reactants, you're going to increase the reaction rate. I mean, I think that one's pretty much a common sense one. All right. Heat them up, speed them up. If we increase the temperature, then that's going to increase the kinetic energy, and it's going to cause the particles to collide with each other and probably with more energy also. And so that would have caused them to react quicker. So that would cause an increase in the rate of the reaction. And I think, kind of a general rule of thumb is that for each 10 degrees increase in temperature, it will double the reaction rate. So that's kind of just a general little term or general little idea of how it affects it. All right, next, and some of these, like we covered in Chem 1, we were like heat them, crush them, stir them, all of those different things are kind of what we're falling back to here when we're talking about that. Remember that the activation energy is kind of the energy hump that a reaction has to get over before it can actually start reacting. So if the temperature is increased, then they're usually able to reach this activation energy quicker, and then that would speed up the rate of that reaction. All right, next one would be the surface area of the reaction. Except for gaseous states or solution, remember we talked about solution, that's usually talking about something that's in a water solution. The reactions kind of occur at the boundary or the interface between the two phases. So if something is done like crushing it to increase the surface area, then it would also increase the rate of that reaction. And it kind of gives you a really cool example here. If you look down at the last sentence, coal dust is very explosive, and yet a piece of charcoal, which is also made out of coal, is not explosive at all. So the difference between those two is just the surface area. Obviously, the coal dust has a lot more surface area, So it can react a lot quicker with the atmosphere or whatever it's reacting with. The next one is a little bit different. We really never talked about this, but adding an inert gas to the reaction does not affect the rate because it will not be part of the reaction mechanism, which right now doesn't mean a lot to y'all, but that's part of what we'll be studying. So like some halogen, if it's added for some reason, that's not going to change the reaction rate. Also catalyst, we talked a little about, we maybe mentioned it in Chem 1, but I know y'all talked a little bit about it in biology too. So remember, a catalyst is something that will increase the rate of the reaction, but it is not consumed, it's not used up, therefore it can be used again and again. It's not really part of their reaction. That's why it can be used again and again. So catalysts will come up in these types of reactions. Some reactions that are catalyzed will occur a little bit faster. And we'll actually be able to see that in the reaction mechanism itself that we'll learn to look at. Yeah, it can. Yes, that's usually what it is. It's written above the arrow. Now, what we're doing with them when we're looking at these reaction rates and reaction steps, it'll be different in that. But yes, if we just had a general equation like we needed to use a platinum catalyst, we would put PT above the arrow. And that shows that it speeds it up, but it's not really used up or it's not really part of the reaction. So that's why you don't put it as a reaction. I mean, as a reactant or as a product. Catalyst is not part of the chemical reaction. This is at the top of the next page. So it's not used up during the reaction. And the catalyst usually participates in the rate determining or slowest step, which once again, right now, doesn't mean a lot to us because we haven't done it yet. But when we start looking at these reaction mechanisms, a lot of things will be dependent on the rate determining step. All right, so there's two types of catalysts that we will be looking at. The first one is a homogeneous and the other one is a heterogeneous. So a homogeneous catalyst is in the same phase as the reactants. So a heterogeneous, and it's pretty common sense, would be in a different phase than the reactants. The benefit of using a heterogeneous catalyst, because it's in a different phase, it's easier to separate it from the products. And a heterogeneous reactant is often more stable and degrades a lot slower than a homogeneous catalyst. So with that being said, when we start looking at reaction rate mechanisms, a heterogeneous catalyst won't show up in those in the same way that a homogeneous reactant will show up. And that's going to be the difference that we're actually going to see and apply to that. All right. So a homogeneous catalyst actually does appear in the rate law, and its concentration affects the reaction. So that's going to kind of be a big thing in this unit. So once again, while it might not make that much sense to you right now, it'll be something that will become important. So those are some different factors that affect the rate. And now we're going to look at the collision theory. That's going to kind of guide how fast a reaction occurs. Let's see if I guess how many of these are going to be on here. Shall I go one more? Okay, good. All right. So the collision theory states that when suitable particles of the reactant hit with each other, only a certain percentage of the collisions actually cause any kind of significant chemical change. So just because a particle collides with another particle doesn't mean that it's actually going to cause a chemical reaction. It has to, first of all, for it to be successful, first of all, it has to have enough energy. And that's one of the reasons when you heat it up, that increases the energy. So that tends to increase that process as far as a successful collision goes. The other thing that it has to have, it has to be in the right orientation. And that's a little bit different than anything that we talked about in Chem 1. Let's see what else I got. So whenever they hit at that moment, then when they hit the Coulombic attraction, they love talking about that, between the bonded atom and the shared electron. So that is what's shared within the electron and within an atom and another atom, must overcome the molecules so that the pre-existing bonds can be broken and new ones can be formed. Remember, we talked about the fact that it takes energy to break bonds. So if it takes energy to break bonds, the more energy that I put in it, the more bonds are going to have a chance to be broken as far as the reactants. And then when those bonds are reformed in the products, then energy is released. All right, I think I kind of already said some stuff about that last little paragraph talking about temperature and successful collisions. All right, so these are all the things that we have to have for a reaction to be successful, or it's called an effective reaction. So the particles must collide. That makes sense. Usually only two particles collide. They have to be proper orientation. So just because some particles hit each other, if they're not properly oriented, where the electrons can have less electron repulsion, they're not actually going to react. And once, like we said, they have to occur with enough energy to overcome the electron repulsion of the valence shell electrons. Because just think, if two things are colliding, they're all going to have electrons, and that's going to actually repulse each other. So the energy has to be enough that they can overcome that and actually collide and actually hit each other. So that's what they're talking about. And if that is possible, then it is called an effective collision. So the new collision product is at the peak of the activation energy hub, and we'll see a picture of that. Well, y'all can already see it. That's your picture at the bottom, and we'll kind of talk about that. And it's called the activated complex. When it's at that point, so it's kind of like at the top right there, it doesn't necessarily have to go to the products. It could fall back to the reactants. So it kind of just depends at that point what energy is involved and how many particles are collided. All right, so let's see what we got on this page. Nothing like, how do you do that one? Let's see what's going on here. Oh, you cracked me up. Okay, this is what I was looking for. All right, so if we got up here, this is where the activation energy would be. Remember, what type of reaction would this be? An exothermic or an endothermic reaction? Would it be anybody disagree? If this is energy where my reactants start, this one would have to be an exothermic, because look, your energy is increasing. So my reactants are at a higher energy than my products are. So this one would have to be an exothermic. But remember, there's this huge hump that although nothing may end up being at that energy when the products are finally produced, it still has to get to that activation energy for it to occur. So this is where we had the activated complex at. What did you say? I'm sorry.
I just misread it.
Yeah.
That was the amount of energy.
But it was flipped.
No, not that it was flipped. I thought that was like energy.
Oh, I got you. So that's what they're saying. All those things talking about collision are happening right along here. Enough energy, orientated the right way, all those things, so they can get past this activation energy and then hopefully fall down to the products. So with that all being said, kind of amazing that we even have chemical reaction. There's a lot of different things that are going on. All right, let's talk a little bit on the next page about those graphs, and then that'll kind of take us to the beginning of the mathematical parts, which we are going to stop right there. So these types of graph are called Maxwell, Boltzmann distribution graphs. So one scientist or two scientists, I'm not really for sure. But your numbers of particles are increasing and your energy is increasing this way. So all of this that's blue or black on yours, these are all the particles that do not have enough energy to react. So you can see there's a lot more that can't react than this little small portion right here, which are the ones that can react. This right here is where your activation energy is. So these particles in the blue were not able to get to that activation energy. So there's no way they could have then, of course, gotten into products. On the other one, you can see there's a T2 and there's a T1. So the T2 has increased the temperature a little bit. And in that process, then it also increased how many particles are now able to collide, get to that activation energy, and then able to produce those products. So that might be a small change in the overall energy, but it gives you a greater number of particles that have enough energy to react and to form the product. So if you had one of these graphs like on the AP test, or if they asked you to make one, you can make a real rough one. What you would need to know is the activation energy. And then once you did that, if this one had numbers on it, you can mark off the activation energy. You could say the ones to the right are the particles that would collide correctly and react. The ones to the left would not. You could even, if you were asked, do a little temperature change. Because if they ask you to make a graph, most of the time they're just looking for a rough graph, like that you have the idea that's going on. So if they ask you to make a graph where you had to represent a temperature change, then you would just need to kind of do this where you represent that the temperature change. So the number of particles that can't react have to decrease a little bit, and the number of particles that can would have to increase a little bit. So I can see that maybe being part of possibly you might see something like that on a FRQ or something like, or a type of question. All right, any questions on that? Yes, sir. Oh, wait. Mhm. No, because that temperature one is just really reflective of the temperature and how many particles are reacting. So like when are you talking about over here on this side of it? Or
So temperature one is the higher temperature.
no, temperature two would have to be your higher temperature. Because look, all of these are the ones that will not react. Okay. So that's why that curve flattened down, less wouldn't react. And this part kind of extended, it got a little higher on the portion that could react. So as you would have to really know what these graphs mean, because like if I looked at this without knowing what it meant, I would assume that all the black part are all the particles that can react, but it's actually just flipped. And what it is all dependent on is that EA, that activation energy. That's like the number you would have to know to mark off on a graph. Anything before that is not going to be enough energy for the collisions to be successful. And then there would be a little portion after that is. I know I know what you're talking about. To me, the graph seems a little bit backwards if you don't really read everything into it. Is that what you're saying? Well, take some time when you have a chance to look over it, and then if not, we can always talk about it some more. Okay, but I do understand where you're coming from. But notice that as the temperature increased, this up here, this on that's your y-axis, that's not measuring energy. So if that's the part that's confusing you, the fact that T1 is higher than T2 on the y, that's not measuring energy. That's just measuring number of particles that can't. This is where your energy is being measured on the x-axis. So that may make it a little bit clearer. All righty. And let me get back on this one. We may have covered everything because we're not going to do that. All right. So I think we're good right there because all that little paragraph below the graphs, I kind of already went over all that we talked about. And then the last bold statement is just, once again, that statement, general rule of thumb, that the reaction rate will double with a 10 degrees rising. temperature. Okay, so we're gonna stop there because after that, it kind of gets into the math part of it. And so I would rather just wait till we get through our other test on that. All righty. Fun times.